Okay, so we'll continue after that. Unfortunately, there was a quite nasty bug in one of the slides that took quite a while to fix. It's now working correctly, so um, the figures should be correct, but potentially there are still a few minor errors. So now we basically covered before this idea in that we have this kind of fundamental problem that we can create this very useful distance map where we visually can see the distances that we're looking at inside the object. But when we try to quantify something out of it, maybe the maximum value has some significance, but everything else that we're looking at is difficult to interpret at the very least. And so one of the things that we can start to do with this is make a thickness map. And so this is taking a step towards chemical or biological meaning, really from the perspective of diffusion sort of processes. And so when you think about diffusion processes, and this comes up in diffusion tensor imaging and a number of other fields, that you have this idea of sort of a particle, and what does this particle locally see? Do you have in its immediate surrounding, how much freedom does it have? And in all directions, sort of what is around it. And so what we do to sort of translate this to the distance map is that we take the object and we find what are the largest spheres at any point that we can fit inside the object. And so spheres is the case for 3D. Circles would be the case for 2D. Distance map or thickness map doesn't really make that much sense for 1D, so we won't talk about that. But that if you have an object like this, so imagine that that's some kind of cell, that you can go through it and at each point fill up a sphere, and what's the largest sphere you can put at that point. And for a point in the middle, it's sort of the same as the distance map. When we looked at the distance map before, we have points here, and this value of 90 corresponds to the largest circle you could put in that region. And so what this has as a primary difference is that rather than just looking at the middle point, you look at all the points. And so this point also can have a sphere inside it that fits, that has the same radius. And so basically any point in this sphere would also have that value for the thickness at that point. And so that doesn't correspond anymore to how far it is away from an edge. It corresponds to what is the largest sphere around it that it fits inside. And so this is obviously ideal for kind of spherical or cylindrical objects because it shows their radius. And so this value no longer corresponds to a distance. This corresponds to a radius of the largest object that fits there. Again, this is also why the distance map needs to be calculated on images correctly, because if your distance map isn't calculated correctly, then this sphere or this thickness also has no meaning. This assumes you have the same distance directions in every direction, and that's quite important to take into account. It's also quite relevant for flow and diffusion because it can highlight bottlenecks in the structure. And so when we go down, we have this sort of image we did before. We've downscaled it a little bit because thickness map is quite computationally intensive. But we fundamentally have sort of this segmented image, a distance map of the foreground, and a distance map of the background. In terms of the algorithm that we use for calculating the thickness map, this looks a little bit different than the ones we've seen before. And so what it does, in sort of layman's terms, is it takes all of the distance values that you have. It sorts them in a descending manner. So it takes the largest distance first and the smallest distance last. If the distance is above 0, it creates this sort of mask of all the points inside its sort of domain. So all the points that are within a distance away from this current point. And it then sort of creates this submap where it says all the points that have a thickness less than my current value are the ones that I want to select. And then it takes all of those points and sets it to that current value. And so here it's also quite important that you keep sort of your distance map and your thickness map distinct. And so here we make the thickness map as sort of a copy of the distance map, as that's your starting point. And then we iterate through it, but we always use the distance from the distance map, not from the thickness map. Because of course, if you use it from the thickness map, you'll end up with wrong results there. Even for small images, this can take quite a long time to compute. So we have it computed here for the foreground and the background. With this package from Python, you can have it show you how many steps it's gone through and what its progress is. And now we can see for the thickness map instead of the distance map, we end up not with a whole bunch of sort of different values that are difficult to interpret, but we have the values here for the thickness of sort of each object. And that by looking at these, we can see that this value is more or less circular, but it's not perfectly circular because there's a lot of these points at the edges, you can zoom in more, where that color sort of changes quite a bit. And that we can see, here is the thickest part of the cell, and then it gets thinner and thinner. And these two cells, sort of the same sort of results. We can then look at this and see, for the background image, how far are things apart? And, how do the spacing between objects look? And so basically what this shows us is rather than just having the distance map, we get an idea for all the things here, they are fairly far away from the nearest object. Whereas, here and other places, they're much more closely packed together. So this can also be done in 3D. We don't have the 3D examples in the notebook yet, but you can do them yourself if you use ImageJ or Fiji. This is a built-in operation to run that's quite easy to do. But where you have for example, here is a foam sample where the segmentation is very poor. So we look at this foam bubble and there's all kinds of holes and gaps, and we didn't do a very good job of segmenting this. And if you would try to do something like erosion or dilation to clean up the image, it probably wouldn't help you that much because it would first of all take a very long time because these images are very large in 3D, and there's so many sort of gaps and holes that it would be very problematic. But if you perform sort of a thickness analysis on the same image, you get to sort of the structure that you are much more interested in looking at, where you can now start to see the size of the bubbles. And the color then corresponds directly to the radius of that bubble. And so here, this example works particularly well because all of the bubbles are spherical. If you get into situations where the bubbles are elongated or different shapes, the thickness map becomes a less reliable tool. But fundamentally, we can see how those results look. So for interfaces and surfaces, many processes happen at them. Even as we calculate these distance maps, it's quite important to incorporate the surfaces and boundaries between them because that's what we're calculating the distances for. If a segmentation is identifying a volume or an area, and so 3D or 2D respectively, then an interface is looking one dimension below. And so, if you have a volume, an interface in that will now be an area where you have two volumes touching. Or if you're looking at areas, the interface of two areas will be a perimeter or a line, so in 2D. So they're particularly important for connectivity, particularly neurons in material science, for coarsening or rheological behavior, and for chemical processes. So surface bound diffusion, catalyst action are also very are both very strongly driven by surfaces. So we'll skip that for now. One of the more important things, I think we have don't have that in there. One of the important tasks for performing this sort of interface analysis is something called meshing. And so when you construct a mesh, you look at very different information from sort of the image data itself. And this will allow you to create a representation of your object that is more or better suited to kind of the reality of the situation. And so particularly when we're dealing with images, it's very difficult to quantify something like how hard is it to turn a pixel off. If we look at the image of the foam, saying how hard it is to turn a molecule of water into a molecule of air isn't something that's very easy to do. It requires an enormous amount of energy to actually make that change. But if we now represent the image in a way that you can think about it as sort of a mesh, you can now focus on how much does it cost to move this vertex a certain amount. And what's quite nice about this is that you now have these sort of basic mechanics models that you can apply, where you can sort of have, a Hooke's model in a very simple approach of this is the sort of length of this vertex or the distance between these 2 points before. And if you change or deform that, that's how much sort of force will be applied by that deformation. And so this can be very useful, as we'll get into later lectures, when you're sort of looking at how do you look at time series, how do you look at objects that change over time. And by creating meshes, which we'll have a little bit of in the exercises, you can create a representation that allows you to look at sort of vertices and points that are connected together and sort of a topology rather than just pixels, because pixels are a very bad representation for most of the things that we're looking at. So we won't get too much into detail for this because this is also something that there are entire courses about. This is the entire basis for sort of finite element modeling, that you're able to take data and turn it into this mesh representation, and how you store this mesh and how you efficiently compress it and how you run simulations with hundreds and millions of vertices is that whole area. But for us, it's just kind of important to understand when you make that transition and why you would leave sort of the imaging domain for solving certain types of problems. So some of the approaches for doing this are marching cubes. So this approach works quite well. You can apply a marching cubes algorithm to a data set and then very quickly see sort of where the boundary of that data exists. Basically what happens is you go through the image one voxel at a time and you look at the neighborhood of that voxel and you try to match it to what the most reasonable pattern inside this collection of cubes is. And so when you have this point here, for example, you look at, this point's on, this point's on, this point's on. Therefore, the most reasonable representation for this region is this sort of slanted surface, where if you have this point on, this point on, this point on, this point on, this point, this point, this point off, then the most reasonable representation is this. And so you can sort of think about it as an algorithm that goes through and kind of has dictionaries of different patterns, and it matches your current situation with one of these patterns in order to decide which sort of cube or set of triangles makes the most sense, which then allow you to get a representation like that. That if you think about a volume by itself, it's not particularly intuitive how you would visualize that in 3D. And if you have a bunch of surfaces, it's then very easy to render those surfaces in 3D. Fortunately, this is also a tool that's very easy to use. So it's built into Scikit image. And it's one of the kind of standard approaches you can apply. And so here, this is just a very simple example where you have a 2D surface that you extract from a very standard object.
Can you export this as a STL file, for example?
Yeah, that's where it gets more difficult. So Scikit image can make basically a list of vertices, faces, normals, and values. And from that list, you can build an STL file yourself. Probably not really what you wanted to hear in terms of the actual utilization of these things. For most, I think if you use tools like VTK, which we'll also come up to more in later lectures. Ooh, that's not very nice. These allow you to kind of build pipelines that have marching cubes as one of the steps inside of them. And so the tools in Python are well suited for sort of fairly small basic data sets. And as you get larger, more complicated data sets, tools like VTK become better suited for connecting a lot of these operations together because they have this pipeline distributed nature which lets you scale the operations more efficiently. There should be one. I'm surprised there's nothing for Python. Oh, there's a. Oh. Okay. Well, so VTK doesn't necessarily make your life simpler. It's probably the reason why Scikit image was made, because VTK is quite tedious to use. But VTK is probably better for doing these kinds of tasks if you want to export it to like an STL format to import into other tools. Because fundamentally what the marching cubes in Scikit image does is it just goes through and creates this list of triangles, vertices, and normals, which we'll see are very useful for doing other kinds of tasks. If you have more complicated images or are more interested in studying sort of the exact surface patterns, there's sort of an extension of the marching cubes algorithm called marching tetrahedra, which take that kind of one step further, which rather than trying to fit a single cube to your object, you can start to fit a tetrahedra. And this can be useful for certain types of tasks and is unfortunately much more difficult to implement and built into many fewer tools. But if you're really interested in what's happening at surfaces and you want a better approximation than sort of this marching cube approach, it can be very useful. So now what we'll get into, and I think these slides work better for this, is this idea of kind of curvature, where it's a clearly related metric to interfaces between phases or objects. It's kind of most easily understood in the 1D sense, and so if you sort of have a line and you want to measure the radius of the circle that matches the local shape of the curve. And so if you have a point here, that radius is quite clearly the same as that sort of curvature in the line. And so, you know, mathematically it's defined as the curvature is sort of 1 over this radius. For continuous problems, it's connected to sort of the second derivative that you can calculate it that way. In discrete space, you have to use different approaches for looking at these kinds of problems. But you can see, at least visually, it appears to kind of try to capture the same kind of information we were looking at with the thickness map. That it's again focused on sort of spherical objects and how do we model what we're looking at with spherical objects. In reality, it's calculated in a very different way. If you think about the curvature of a box, the curvature of the box is 0 on all the faces, and then extremely high in the corners, where the thickness map of a box and the thickness map of a sphere don't look hugely different. That you have basically a large thickness in the middle and then smaller thicknesses as you get closer to the edges, but that you don't have that huge sort of gap between the edges and the middle. So in terms of looking at curvature, the starting point for doing this is really creating a surface. And so if we have this sort of like sample object that we looked at before, once you've created the surface, you can calculate at each point on the surface something called a normal. And so this is the vector that's perpendicular to that plane at the surface, going away from the interior of the object. And so you get a fairly basic representation of what that looks like on an image here. And the pair view exercise, if you're interested, we'll go into that. We might make a Python exercise that does this, but it hasn't been done yet. So there's nothing for you to work on in Python. It's just more sort of conceptually that you can appreciate what's happening. So in 3D, this is, of course, a little bit harder to define. If we go back to the sort of circle idea along a curve, that's what we did in sort of 2D. In 3D, we have a more difficult task because there's curvatures in sort of both directions. And so when you think about kind of this type of shapes that are possible, which is probably easier than thinking about the math, at least initially, that you can have a sphere where you sort of have a curvature both going in the same direction. You can have a saddle where you have sort of the curvature going this way in one direction and sort of the other way in the other direction. And then you can have sort of the opposite of the sphere, where you have sort of a dip in both directions. And so for this, what you define is you define sort of a surface normal, and you have sort of many curvatures depending on how you rotate the plane that you're looking at, and that we define this angle theta, about which the plane containing sort of both the surface and the normal can be freely rotated. And we define two curvatures as being sort of the K1 and K2. And K1 is the maximum value of the curvature that you have here. And K2 is then the minimum value. And so in a sphere example, K1 and K2 would probably be very similar. In a saddle, K1 would be large and positive, and K2 would be large and negative. And in sort of the dip or divot, they would both be negative. So then you can, from this, define sort of two simpler ideas. The mean curvature, which is where you add the two, take the average of the two principal curvatures. And so if you think about the case of a saddle, this would be potentially 0. And in a sphere, potentially the same as K1 or K2. And in a divot, the same. And then the Gaussian curvature, where you sort of have the product of these two. When the Gaussian curvature is sort of positive, they're both in the same direction, and when it's negative, you have some sort of saddle-like shape. And so this gives you some kind of basic intuition for how these terms are used, and mostly for kind of interpreting their meaning. So if we look at sort of 3D examples of curvature, we have some images from ParaView here, where you can see the sort of the mean curvature or the Gaussian curvature. You have fairly low values sort of along these surfaces, and then at the edges you end up with very, very, very high values. And so you end up, in a lot of cases, dealing with the problems of you have a finite object in a finite space, and a lot of the points are discrete. And so when you look at curvature, as soon as you run into these kind of boundary issues, you tend to have the most extreme outliers in what you're looking at. Gauss curvature is even sort of more pronounced because you're now looking at the product of these two terms. And here you mostly just see the artifacts at the edges. And so when you calculate these things, you need to be sure you're properly accounting for these boundaries and that your results are not affected by the fact that you have more exposed surface in one image versus the other. But one of the nice things about curvature is that you can sort of normalize it. And so when you look at the curvature, it's related sort of 1 over the radius. And so if you multiply it by the radius, you now have a shape sort of independent, or the average radius, you have a shape independent way of characterizing how the objects look. And so if you're thinking about sort of an experiment where you have spherical particles that are annealed into a mesh of balls, you know, we had that example before where we were melting the things together and we used component labeling and distance maps to sort of quantify what was going on. And we can do the same thing with curvature, where we can see sort of how well annealed are these objects, where the focus will be then here much more on where are those interfaces and where do the objects go from being sort of sphere-like to saddle-like, which is what happens when the sort of 2 particles join together. And so, you know, we used a distance map earlier because it was less sensitive to those changes. And we would then use this if we wanted to be even more sensitive to those changes than something like component labeling. And so you can look at that distribution in time and see how those things change. And some of the references at the beginning go to that in much more detail. But it's just a concept to generally be aware of, potentially data sets to play with as well if you're interested. So characteristic shape is really trying to normalize these so you can talk about how do the shapes actually look. You know, does it go from being a more spherical object or more spherical objects or more saddle-like shapes, and how do these shapes change independently of the size or the scale of the object. We can also do the same sort of analysis with a thickness map where we normalize by the average thickness in the image, and then we see how that distribution changes. And so do things become more spherical or less spherical? One of the things to be very aware of is that when you do these normalizations, you have to be very careful about discretization problems. And so if you have a shape that's 1 pixel large, you know, the thickness of this shape will be 1. The curvature of this shape will be, you know, perfectly spherical because that's all you can be with 1 pixel. And so as that object grows, if it becomes 2 pixels, by definition, it's now all of a sudden incredibly anisotropic. It's now has very many different curvatures. And that if you're looking at very small objects, you get a very poor representation for what that actually looks like. So if you just have 1 object or 1 pixel-sized objects, you'll end up with everything being perfectly spherical, even though in reality they probably are not. And so a lot of times you'll see studies where they show that sort of objects become more spherical as they get smaller, when in fact this is just really an artifact of the fact that if you only have 1 pixel, all you can be is perfectly spherical. So it's kind of take-home messages. It's a useful tool, particularly if you're looking at interfaces. And you know, you can provide some of these visual indications. You can make very nice colorful maps, but it's very sensitive to small changes in your data. And so one of the things we don't show here, but if you know you have small amounts of noise, you know, if you go back to this example here, you know, if you add a slight bump to this surface, that curvature can wildly change at that point. You know, just moving 1 point here a little bit closer in would make this curvature, larger. And so it's very sensitive to these sort of small fluctuations. And so if you do have issues with noise in your data, curvature is going to make this much worse and much harder to see the effects you're really interested in looking at. But there are many groups that use these tools, and if you have very high quality imaging data, they can be very useful. So there's tons of other techniques that you can try. One of the easiest ways to see this is sort of by looking through Scikit-Image or looking through Fiji, that you have these folders full of plugins, 9 as well. that do all kinds of weird analyses. So you'll have tubeness or surfaceness. There's directional analysis. There's 2-point correlation functions, fractal dimensionality. And if you even start to look at any of these things in detail, you'll find that there's hundreds of metrics that exist that you can calculate for any given object that you're looking at. So it's probably worth investigating in your field what the common techniques are, and maybe some of these other techniques to see if they apply well to the problem that you're looking at. But unfortunately, there's way more tools available than there is time to implement any of them. And so you have to sort of be very careful with investing too much time in a certain type of analysis because, surfaceness or tubeness, in the paper they found data sets where it worked really nicely, but if you try to apply it to your own data sets, it's very unlikely that they work as well. And so you'll have to sort of balance how common is that in the field, how important is that for the project you're doing, and if they sort of make sense. So for texture analysis, as sort of the last part here, it's this basic idea of sort of looking at patterns in images, and that you have, for any of you who've used the 9 tools or experimented a little bit more with the scikit image sort of feature analysis, you'll see that there's a whole number of different analyses which can be done. And so when you do shape analysis, when you give it an intensity image, there are lots of different things it will do or that are possible to do with this intensity image to sort of describe what the object inside looks like. So you'll find that, you have everything from very basic things to sort of, entropy, variance, difference entropy, measure of correlation 1, sum average, sort of all kinds of different values that you can look at. So if we look at sort of sample textures here, we come up with sort of 6 different random patterns that we have where, maybe your goal would be to try to quantify different textures that you see. If you were a clothing company and you wanted to, measure how much of, how many people were wearing plaid patterns, how many people were wearing checkerboard patterns, things like this, that maybe you'd want to build something that classifies that well. And so, if you have a very good segmentation algorithm, maybe you can segment someone's shirt very easily, but then quantifying what's actually on that shirt becomes a bit more difficult. So when we look at the intensity or the intensity distribution for those patterns, we see sort of, a histogram with a bunch of peaks on it, but nothing that's sort of very clearly identifiable as that's how we would classify one pattern from another. They all kind of overlap, have the same gray values as we see there. And so one of the things we can do is make this sort of co-occurrence matrix. And this is basically where we say, at any point or any intensity value, I and j, what's the likelihood over sort of all possible values in the point, in the image, of given a x naught and y naught, or sort of x and y, that has a brightness of I, what's the likelihood that a point at x plus delta x and y plus delta y has the brightness j? So I did not explain that very well, but basically what it's trying to do is sort of give you an idea of, if I know this about this point, what sort of information can I extract about the points around it? And so, for example, if you're a point that's turned completely off, what is the likelihood that the points around you are turned on? And so this matrix gives you sort of a basis for trying to quantify things like pattern into sort of a single table. Whereas if we go back to this image, if we see this point here. So this point is turned off, it's dark. What's the likelihood that points around it are turned on? And we see that points directly above and below, so sort of delta y, are also likely to be turned off, so they're very unlikely to be turned on. But points to the side are very, very likely to be turned on. And so what this co-occurrence matrix kind of serves as is sort of an average over your image. So sort of how can you describe the whole image in sort of one little pattern? And that we see for these patterns that is sort of a useful description. So for here, when it's completely off, the points above, down, left, right are likely to be on, and the points diagonal are likely to be even stronger. And so using that as a basis, we can start to quantify this pattern into one single matrix that we can then analyze in more detail. So we have a co-occurrence matrix. It's similar to the two-point correlation function that we sort of mentioned before and briefly here as a very useful tool that's very commonly employed by physicists and sort of material scientists in the theoretical world for modeling complex materials. But that basically it gives us this 4D representation that we can look at, and we can then discretize this representation into different bins that allow us to classify these patterns differently. And so we can calculate this matrix for each one. So each row here represents a different one of the patterns that we showed before. And each column represents a different I to j value. And so here, if you're going from sort of 1 to 1, that's what the pattern looks like. You know, all the ones that are blank are ones where you don't have any points that are going from 1 to 1. And that we can see different ones of these fill different numbers of these patterns, and that by looking, you know, how many of the pixels are filled or what's the relative count in different parts, we can start to analyze these images in more detail. That's not a very helpful representation. By looking at sort of simple correlation, if we look at sort of the mean difference, instead of all the IJ pair possibilities, we can collapse this down to sort of a single image. And so what we can see here is that, you know, for those patterns we had before, we now get an image that summarizes that pattern very well, rather than these sort of 4D representations that are quite difficult to look at. And so here we can see each one of these represents sort of a simple pattern that you're trying to quantify from that image, so that rather than having all the pixels, you have just a few. Yeah?
So, for example, if we would have some structured noise, could we use this texture analysis to then filter it in a convolution kernel or something?
Yeah, so this is where the texture analysis sort of, it doesn't break down, but what texture analysis is sort of built up to do is given a region of interest to quantify it out as sort of a single point or single value. So if you had structured noise, what you could potentially do is find out which of these texture parameters most strongly correlated with it, and then maybe excluding samples that have too much textured noise based on this texture. But to use the ideas from this to then try to go back and fix the image, I think would be quite difficult, because most of these things are just set up. I mean, as you can imagine, this sort of 4D representation, particularly of large images, is incredibly computationally expensive to compute. And so all the tools that exist to do this kind of analysis are set up to sort of take a region of interest and spit out a table full of values. But potentially looking at things like 2D correlation functions, establishing that, and trying to identify where things fit up or don't fit into that pattern well, and exclude them might be worthwhile. I think it'd be quite difficult to say, this is the pattern I don't want, and now I want to remove it from the images by somehow performing a convolution there. Unless you could say, if you go back to this initial definition here, if you know that there's certain forbidden transitions here. So if, for example, you know that if the so I is 0 and j is 255, so that if you were looking at something like this, and you know that any time this point's turned off, there should never be anything above and below, that you could apply that rule to kind of an image. But taking the full texture analysis and then using it to try to fix the image would be fairly difficult. It would probably be more useful to sort of sort the images into categories and say these are really good ones and these are ones with lots of noise, and so we are less interested in the ones with lots of noise. Or these are ones that require, you could have a bank of different filters, and for the ones that have a lot of structured noise, you use a certain type of filter, and for ones that don't have very much structured noise, you use a different one. So you'd probably use it more in a decision process than in actually sort of a reconstruction process. But yeah, so you can also calculate these coordinates in sort of radial space if you're looking at patterns that are supposed to be sort of either radial, polar, or sort of spherical harmonic correlations in your system. This also then fits with a lot of the two-point correlation function material, where you can sort of look at a different distance and different angles from your point. What do you expect the values to be? To make this all a bit more concrete, there are, Scikit-Image has some nice tools that do the basic analysis of this. So there's a notebook, it's also referenced in the links, where we take these images we had before. And so what we want to see is are there any clear differences between the texture that we find in the mitochondria and the textures we find in the background. And so we have sort of an image, a segmentation, an overlay of sort of what regions are we actually looking at. We see for this image a threshold is very difficult, which is why it's a very nice data set to practice on. So what we do is we make a bunch of tiny tiles. So here we divide it into lots of small, 64 maybe tiles in each direction. So each one of these values represents a different tile along the axis. And then we calculate the texture on each one of these tiles. And so we use this sort of coincidence matrix that we talked about before. We can sort of define the parameters that we want it to calculate, tell if it's normed or symmetric. And then we keep, for example, sort of the dissimilarity and correlation, which are some of these values you can extract from that matrix once you've defined that coincidence. So once you've done that, you can extract any of these values. It's not really worthwhile to spend too much time explaining what all these values could mean, because they're anyways not particularly interpretable. It's much more useful to just have a feeling for which values are more relevant for your problem, because all of these things are sort of from the bowels of computer science and computer vision that were made sort of decades ago when people were trying to optimize theoretical problems, and many of them aren't particularly relevant for real noisy images. But if you're interested, it's certainly worth reading more about. But you can then sort of create this whole array, and what we do is we run through all the tiles and sort of calculate what's the dissimilarity inside this coincidence matrix and what's the correlation value. And so that we see here, here's the original image. Here are sort of the regions. This is the dissimilarity value at that point in the image. And so when you calculate dissimilarity inside that tile that we defined, this is what value you get. And this is then the value for correlation. And so these were sort of two metrics that we decided to pick out. And that what we can now do is make sort of a full table out of this and say, you know, if this is inside a mitochondria or a segmentation of a mitochondria, we say it's foreground, and otherwise we say it's background. And that we record the intensity, the standard deviation, the correlation, and the dissimilarity. So we can now plot all of those points and start to see in sort of what's called a pair plot, which we've also looked at before, kind of what the differences between these values are. So, you know, we see from a intensity perspective, there's almost no difference between the mitochondria and the non-mitochondria. They overlap perfectly. From a standard deviation, there appears to be some separation, or sort of correlation overlap perfect. Oh, sorry, I read them in the wrong order. From an intensity, there's some difference. From standard deviation, there's very little. For dissimilarity, we see sort of two peaks there. And for correlation, we see very little difference. And so correlation doesn't tell us that much about whether it's in there, but dissimilarity seems to give us a nice index that we could potentially use to separate these things. And so we see that texture analysis here gives us some potentially useful channels that we can combine with sort of more standard analysis in order to try to classify these images better. And so you have this whole range of, you know, dozens, if not hundreds of parameters. If we go to the Radiomics package, which is very similar to these kinds of analyses that are all based on this grayscale correlation matrix. That we have sort of images that you put in sort of a very marketing fashion. Images that you put in along with sort of a segmentation of, in this case, the tumor, a number of different filters that you can apply. So here, looking at sort of more than just the initial image data and sometimes sort of square root, logarithm, Laplacian of Gaussians, sort of a number of different approaches. And then applying these feature extractors where, you know, you have the first order, which are sort of the mean and standard deviation that we talked about. And then these sort of, you know, coincidence matrices, and there's, you know, two other techniques as well that are also very complicated to implement, and that you have these nice tools that make it easier to actually run this processing. And I'm not sure if there's anything value on this video. Probably not. But that, yeah, so you have fairly easy notebooks for doing these things. Fortunately, none of them are very visually appealing. But you have a whole number of these texture analysis tools available. And as we saw sort of in this notebook, they can give you ways for better differentiating between different patterns that you see in your images. And so it's a whole field to sort of explore. It's also some of the things that are being done with kind of high content screening now, that you can use a texture analysis to describe sort of healthy cells from unhealthy cells, how things are kind of normally distributed, and get a feeling for those kinds of analyses. So yeah, are there any questions on that so far? I think we're done now.